Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA is a place where if you don't invent the internet, you only get a B.
A DARPA program manager quite literally invents tomorrow.
Coming to work every day and being humbled by that.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
Hello, and welcome to Voices from DARPA. My name is Stacy Wurzba, and I'll be your host. For this episode, we sat down with Dr. Leonard Tender, or Lenny. Lenny joined DARPA in January 2023 as a program manager in the Biological Technologies Office. His research interests include developing new methods for user-defined control of biological processes and supply chain resilience. He earned a bachelor's degree from MIT, a doctoral degree from UNC Chapel Hill, completed a postdoc fellowship at UC Berkeley, and served as a visiting scientist in the Stanford University Department of Chemistry. He co-founded the International Society for Microbial Electrochemistry and Technology and is a recipient of the Arthur S. Fleming Award, which honors outstanding federal employees. But to hear him tell it, that's all fairly standard.
I did the normal routine undergraduate, graduate school, postdoc, and then I was at the Naval Research Laboratory for 24 years right here in Washington, D.C. The Naval Research Laboratory is the Navy's in-house national laboratory. And I was a principal investigator and became a branch head. So I had been a DARPA PI twice in my career, very, very early on, and it actually launched my career. And then later in my career, around 2017, 2018 or so. There are a number of people who have gone from the Naval Research Laboratory to DARPA, and I had engaged with one of them and started having discussions and realized there's a lot of overlap, and I thought it'd be a really great challenge for me to take on. My background, my formal training is in electrochemistry, which is studying the interaction of electrons and chemicals. But during the course of the 24 years I spent at the Naval Research Laboratory, I started looking at how microorganisms are essentially little electrical machines and applying the tools of electrochemistry to study them. All living organisms fundamentally require a flux of electrons in and out. And so for us, when we ingest food, we're essentially ingesting, say, glucose, which is the simplest case, and we take those carbon atoms and ultimately we remove electrons from them, and that becomes the carbon dioxide that we exhale. And a lot of the processes that go on in our body are about moving those electrons around and stripping off the energy. And microorganisms do the same thing. That became, for 20 years of my life, in fact, my first funded effort was a seedling effort from DARPA to take the very first steps at exploring that concept. And I could say that everything else that followed in my career for 24 years at the Naval Research Laboratory was based on that first set of experiments and sort of pioneering, understanding how microorganisms, how we can feed them electrons and pull electrons off of them using the tools of electrochemistry. And so towards the very end of my career, I started looking at organisms that are involved in infection, pathogenic organisms, in particular wound infections, and understanding that when you have a wound infection, that means is that you have a wound and it's been colonized by organisms, and the organisms disrupt the normal healing process. And I wanted to really understand how those organisms can live in a wound. So using the tools that we developed in working with some really great collaborators, in particular Professor Diane Newman from Caltech, who is an expert in these type of organisms, we figured out how the microorganisms are essentially breathing, how they're getting rid of their respired electrons. And we started wondering, well, would that have implications for wound infections if we can start to sort of disrupt that process?
Disruption is an accomplishment DARPA prides itself on and constantly strives for. While disruption of the wound infection process might not seem immediately important to national security, it can be a matter of life or death.
Even in our last major conflict, so Operation Enduring Freedom, Operation Iraqi Freedom, even when we can get the injured warfighters off the battlefield into high-level care within an hour, we were experiencing something like 27% of those people were experiencing debilitating wound infections. And so that's under really great conditions. Now we look at Ukraine, for example, and we're seeing 50% wound infections. And of course, in Ukraine, the difference is they're not able to get people out as quickly as possible. And then on top of that, we're seeing high levels of multi-drug resistant organisms, the whole antibiotic resistance, right? So unfortunately, war is a big driver of antibiotic resistance. And we're seeing right now in Ukraine is very high levels of antibiotic resistance. And so right now, the standard of care when a warfighter gets injured in the battlefield is you administer high dose antibiotics right away. There's two problems with that. The first is that, well, we're kind of running out of time on the antibiotics, right? At some point, a lot of them are just not going to be useful. Secondarily, there's a lot of good organisms that are actually, if not benign, actually beneficial to the wound healing process. And if we're knocking everything out, that's not good, right? And there's nuance in there in how you define infection, because all wounds become contaminated with organisms. In fact, many wounds will become very contaminated, have a high loading of microorganisms, but they'll continue on to heal well. And we don't want to mess with those wounds, right? It's the ones that the wound healing begins to fail. Those are the only ones we want to go after.
The Bioelectronics for Tissue Regeneration program, or BETR, takes aim at these wounds with the intent to create what is, essentially, a smart bandage.
BETR was a program that I took over when I arrived at DARPA, and it was led by Paul Sheehan, who was the program manager that I knew from NRL, who came to DARPA, and then he left shortly after I came and took over his program. And so that is a program that also is looking at wounds, non-infected wounds, but asking a fundamental question is, can we monitor a wound, the healing process in real time, and then interfere with or reprogram the natural healing process to either have the wound heal faster for a simple wound, or for a more complicated wound, have it heal better. For the former, the simple wound, you can imagine, say, someone's had a pretty invasive surgery, right? And you have a big, incision on your chest. Well, imagine if you can apply a bandage, it's going to make it close up a lot faster. That would have tremendous payoffs in terms of just getting people out of the hospital a lot faster, recovering a lot faster. For the latter, in terms of the more complicated wounds, for example, one of the wounds that soldiers, warfighters experience, what we call volumetric muscle loss wounds, where you have a blast and essentially, it is, I guess there's no other way to say it, a big part of a limb, say a leg, is gone, and you lost a lot of muscle and nerves and blood vessels. We have evolved naturally for those wounds to scar over, and scarring is sort of a way of sealing the wound to minimize infection. Imagine if you can reprogram that wound with a bandage or a dressing that is super smart, so that it reprograms it not to scar, but to actually allow for functional tissue to regenerate and to replace the muscle. And we actually have performers who have done both, and it's super, super exciting.
Now, that's not to say that you can go buy one of these bandages at your local pharmacy today.
Developing medical device technology is a very long process. And what we do at DARPA, and really any activity, is really de-risk a concept. And so when BETR started, the notion is, can we understand a wound physiology at a high enough level and then actually have the tools that we can actually incorporate into the bandage to sort of reprogram the healing process? And so we're talking about developing a whole new set of sensors that are monitoring. And the wound's a very complicated environment. You can have something like 4 different dozens of cell types that are all interacting, in a coordinated, orchestrated process that's changing over time. And so we have to be able to monitor all that. And then can we know when we can intervene, right? And so, for example, one team built an incredible digital twin, really modeling the whole wound process, getting all the way down and understanding how all those signaling molecules and all those cells interact with each other, and finding those sort of points that if there's like one signaling molecule at this one time point, if we can just adjust it at this level, this can have a profound impact.
A bandage, sensing, analyzing, and treating wounds without human intervention or additional computing, sounds like something straight out of Star Trek, but it's being made possible today.
So a big component of this is that it's completely closed loop control. So you have your sensors, you have what you're sensing, you have different treatment regimes, methods of treating the infection that are embedded into the device that you can control the release of and regulate the administration of. And that's all going to be controlled through a closed loop control onboard a device. In addition to the technology development and the commercialization and regulatory strategies and all that stuff, we're challenging the people to also think ahead and say, well, imagine that, you're wildly successful, but then you have to have all this follow-on funding, and then you can get the clinical trials. The end product has to be something that is actually useful, right? And we want it to be useful in the battlefield because when a warfighter gets injured, the infection begins, the process begins there. As soon as the skin is broken, the microbes start contaminating the wound, right? It has to be practical, in terms of being useful in a very, very forward environment. So it can't be extremely delicate. It can't rely upon a huge instrument in an analytical lab in a hospital somewhere. Cold chain, it could be a problem. And then, it has to be manufactured at a reasonable cost. We de-risk the concept. And we're actually at the point now where one of our performers is doing the first in-person clinical trials for not the whole bandage, but for the ability to monitor in real time how the wound is healing, and also to actually have the sensors all working, but actually use machine learning, training on the sensors to say this is how the wound is progressing in time, which is a huge accomplishment. There's a number of small companies that have been spun up and spun out as part of this effort. And DARPA is very big into that, having companies being formed by the teams as their work is progressing to help with the commercial transition, because we're focused on delivering these technologies to the DoD, to the warfighters, but wound healing is a huge national problem. The biggest type of wounds we deal with as a nation are diabetic foot ulcers, costing hundreds of millions of dollars, if not billions of dollars, to Medicaid and to the VA. And so it's a different type of wound. The diabetic foot ulcers are more chronic, but there's a lot of overlap in terms of what's going on. And so we're driving the transition of this technology so that market then can eventually feed into the DoD.
DARPA's pretty much done with BETR now. Other groups are taking over. So Lenny figured it was time to revisit something put on the back burner when BETR first got started.
When that program was pitched, everyone recognized that wound infections were a big problem. But the previous program manager and the leadership of DARPA decided that just handling the wound by itself, the wound healing without infection, was a hard enough problem. But overlying the infection would be insanely difficult. Well, 4.5 years later, we've made tremendous progress on that ability to monitor and reprogram the healing process to a certain extent, which is very exciting. And so now the time is ripe to build upon the lessons learned and to add in the infection component.
This is where Lenny's new Bioelectronics to Sense and Treat program, or BEST, comes in.
You imagine a war fighter that's on the battlefield who is not severely wounded. I mean, if they were here in Arlington, Virginia, they'd go to the hospital. But when you're on a battlefield, they can get back up on their feet. If you can get that wound, the bandage on and monitor for infection, that warfighter can return to operations. But more likely than not, given the insanitary conditions, and then also the stress that they're under and how compromised the immune system is going to be, they're going to be very susceptible to infection. But if we can stop that, then they can stay in operations, right? And then we have the whole other cohort that are, for example, the ones with the bigger wounds are going to be flown out. Just managing the wounds if they're infected requires orders of magnitude more caregiver attention, expense. It's traumatic for the warfighter. It can mean the difference between amputation and not amputation, or where an amputation occurs. And so being able to just have technology that can automatically remove that concern of the infection would be very powerful. And so that's the goal of that program. So part of the capability is that it has to be adaptable for variability in people's immune response. And so ideally the way this would work is you'd be looking for signatures of what microbes are there, but also on how the host is responding. There's a lot of overlap there. It could be, for example, that how the host is responding might tell you all you need to know. It could be which organisms are there may tell you all you need to know. But people, their immune responses are very different, particularly people with diabetes, for example, but also war fighters. You take a young, healthy person in their mid-20s here, in Arlington, Virginia, and they get into an accident or something. Okay, but if they're on a battlefield and are dehydrated and in shock and stress, if they're experiencing polytrauma, their immune system is going to completely be out of whack. And so we need to be able to adjust for that. A lot of that is overlap with the BETR program. Part of the big accomplishments of the BETR program is being able to monitor the host immune response, and because it's the immune response which is driving the healing process. Being able to monitor that really gave us the mindset, the framework to say, well, we can do essentially the same thing for the infected wound. Of course, it's not exactly the same. And in fact, it's going to be very different because of how the organisms affect the immune response. The actual programmatic timeline is 3 years, looking at 2 phases, a 2-year phase where we're looking at independently developing the monitoring capability and the treatment capability, but doing it in a manner so that in the 3rd year they can be integrated together. So they have to be coordinated. And in the 3rd year is bringing together the closed loop control. It is a DARPA hard program. in that there are pieces of technology out there that appears could do the job, but there isn't really the complete package. None of the pieces can do it as well as we're going to need it to do separately. And then thinking about tying it all together in the closed loop control is going to be a pretty awesome heavy lift. A lot of work goes into really all DARPA programs to make sure that you are tying it to a pressing problem. We have in the building incredible people who are very connected within all their different branches of the military and are very enthusiastic and very effective at brokering relationships. And so we have a lot of relationships that they broker. Working with our team is Uniformed Services University, for example, and Walter Reed, for example, among others, Lawrence Livermore National Laboratory. They provide certain subject matter expertise. We have what are called SMEs that provide us a lot of expertise in terms of how we rigorously monitor and actively manage the program to optimize the opportunity for success, to maximize the output.
Speaking of maximizing output, there's another side of Lenny's program portfolio that seeks to do just that, by finding value and utility in what's previously been seen as detritus.
There's other areas that I'm exploring that biology is a really good solution set. And so one of them is biomanufacturing, which is this notion of making useful materials out of available waste streams, feedstocks. We had a program that has just ended recently called Resource and was looking at whether or not it's feasible to take waste plastics and then convert them into useful materials, specifically foods, oils, lubricants, and to do it in austere and remote environments and do it with low energy input. And it turns out that biology can play a very important role in that. Biology is really good at transforming one set of compounds into another set of compounds through microbial metabolism. And so we're actually very successful in that program.
Another of Lenny's programs in this area seeks to harness energy from the ocean. That's the Biological Undersea Energy Program, or BLUE.
So BLUE is about determining whether or not an ocean-deployed sensor can actually filter feed on dissolved organic matter in the ocean to generate electrical power. And so the background on this is a look at filter feeding animals in the ocean. Say, take a dolphin, for example. And the dolphin is eating fish. We're not going after fish for sure. But a dolphin can eat about 30, 40 kilograms of fish a day. And a dolphin can live about 40 years. And the average output, if you average how much power they generate over 24 hours, is about a kilowatt. So if anyone's an athlete out there, if you're like an avid bike rider and you know how much wattage you can put out, peak wattage or wattage over ride, a dolphin's putting out 1,000 watts, essentially 24/7, right? And so all that fish that they're eating ultimately is the foundation of all that is just the dissolved organics that are in the ocean. There's a lot of biomass that's very small, below a millimeter in diameter. A lot of it is this runoff from rivers into coastal environments. You have phytoplankton blooms and et cetera. And it's a massive, massive, massive form of carbon that's involved in carbon cycling, biomass cycling on the planet. And so it's a fundamental question is, can we take oceanographic sensors, which the Department of Defense uses a lot of them, other agencies use a lot of them, industry uses a lot of them. They're battery powered. The batteries run out pretty quickly. And then the logistics of either replacing the batteries or replacing the whole devices is very daunting. And so essentially they're very underused, right? If you can replicate that capability of converting that biomass into energy, which biology does, then that's like pretty cool because you could have your device being powered for very long periods of time, far longer than possible batteries. That opens up a whole range of possibilities. And so we have two teams that are now working on that. They are different variations of what are called bioreactors. It's about replicating what goes on in our GI tract or the GI tract of an oceanographic animal like a dolphin, or really the nucleus of that idea came from whales, which are amazing filter feeders. And, converting that biomass into chemicals that then you can use to then generate power. In our case, we want to convert them into molecules, for example, that you can use a fuel cell to generate electrical power, but there's other pathways to do it. And so that's a program that's just starting. We have a couple of teams that started late last year and getting up and running pretty quickly. And it's a thrill to see that. We're targeting 10 watts, then 100 watts of power. And so those seem to be very low amounts of power, but in terms of having an oceanographic sensor, they're actually pretty high, and that's average power over time. And so a lot of oceanographic devices that, monitor weather and environments and stuff. Those are battery power and they get deployed and then retrieved and then deployed and retrieved. We can power something like that and definitely it'd be really pretty cool.
Not one to shy away from a challenge, Lenny continues to explore new avenues for biological technologies.
I'm thinking very hard about a future program in applied quantum biology. Quantum mechanics, it turns out there are a number of physiological or biological processes that exhibit non-trivial quantum mechanical effects, which is really hard to do non-biologically, but biology seems to do it in noisy, messy environments and at room temperature. And so one of the things we're asking fundamentally is, can you make a quantum computer that would operate at room temperature under noisy environments, which we can't do now, drawing from biology that seems to exhibit some of the necessary properties that would require. And so there's a case where biology may be a unique solution to an interesting problem.
Unique solutions to interesting problems is sort of what we're all about here at DARPA.
This is the most exhilarating experience I've ever had professionally. All programs start, with a blank page, and the program manager is thinking about them and engaging with their team and in the leadership of the office. And if you're successful to get it through and get it funded, then the standing up there, especially when you have like a kickoff meeting where you're in front of it, performer teams, is so exciting when you have the performers there, and it could be the professors and the industry people and the small company people and the students, the postdocs and the graduate students and undergraduates. And it could be, 50 people there. And then you have the team also that as part of the government team who's helping us, the subject matter experts from, for example, from Walter Reed or from the Uniformed Services University. It is such a rush. And then we typically have every 6 months, all the teams across the whole program will meet and present, have a review. And when you realize that they're all here working on a concept that you developed, there's nothing really like that. And then on top of that, just the great support that we have. I'm a bit of a ringleader. I'm a bit of a portfolio manager. I have a great team of technical experts. They're super smart and hardworking that work under us to help us really rigorously, put up ideas and then monitor them. And that whole dynamic and interaction is really incredible. And so I would challenge anybody out there, especially if because I'm biased, I'm in the biological technologies office. If you're at a point in your career where you're like, wait a minute, if I can really have an idea that if I can get the resources and the right people to do it, that could just really disrupt or blow up the whole field and have huge impact. We talk about impact in terms of national security, and that has many ways of doing that. But if you're some point in your career and you're thinking, wow, if I can really push an area and have a big impact, and I think I have an idea, give us a try. Drop me a line.
That's all for this episode of Voices from DARPA. For more information on Lenny, any of the programs we discussed, or how you can get involved with the agency, check out the show notes or visit darpa.mil. As always, thanks for listening.